Yeah, hello. It's an honor to speak here. Um, I was wondering, so I read about the moral implications of the many worlds theorem. I was just wondering if you had any thoughts on that.
Yes, I think the only moral implication of it that's different from what morality was before one knew about it is that one ought to advocate it. That it is morally wrong to insist that it's false.
Sorry, I meant more that so do we have to start worrying about all these other possibilities?
Yes, no. So I'm saying that we don't have to worry about those because it's interesting. I'm often asked that question, but in two different forms. One form is saying, well, since you know that every time you drive out in your car, you will necessarily run someone over in some universe, so shouldn't you be more reluctant to drive a car? And the other is, well, whenever you run someone over, they always survive in some universe, so maybe you should be a bit less, worry a bit less. So I think the quantum theory of probability and decisions, which comes out of the Everettian quantum theory, tells us that precisely that, well, at least when we're doing decoherent things, so it wouldn't necessarily hold during my thought experiment, but when we're doing decoherent things, we should attend to probabilities exactly as if the outcomes were determined by probability with the Born rule.
Mm-hmm.
So it should not make us more reluctant or less reluctant to drive a car. What happens when we are fully uploaded into quantum computers and then are thinking we're thinking coherent, quantum coherent thoughts? No one knows yet, I think. Certainly I don't.
We have a question from Babak.
Yes, thank you. And hi, David.
Hi.
I was wondering how you would explain the quantum Zeno effect or paradox, however you want to call it, within the Everettian quantum theory, which, yeah.
Yes, so do you mean the actual Zeno effect, or do you mean the Elizur-Weidmann bomb phenomenon?
Oh no, so I mean the effect being, or the watched pot effect.
Yeah.
Mm-hmm.
Well, that's a case where one is it's another experiment that confirms the Everettian quantum theory. What one is doing is one makes a measurement which is overwhelmingly likely to have the answer A and has a very low probability of having the answer B. Then one does it again, then one does it again, and so on. And classically, the probability of getting a B would go up, actually quantum mechanically as well. But mm-hmm. you can arrange, but because quantum probabilities add up in a different way from classical ones, you can arrange so that in the limit, B will never happen. Mm-hmm. Or will happen with an arbitrarily small probability. So that is simply again, I think that's better understood in the in Everettian quantum theory, because you are simply putting yourself in a larger and larger fraction of the universes.
Right, thanks. Faye?
Hi, Professor. I'm doing quantum thermodynamics, and someday I explain the multiverse and quantum computation speed up to my friends who are doing arts, and they take a very different viewpoint of it, and they ask a question that concerns it a lot. They said that would it be that we steal resources from other universes to speed up the algorithm we have at this universe? So this concerns me. Is it a collaboration between universes to make the computation faster, or just a computation between different universes. This perhaps correlates with your conservation laws between universe. I noticed that there is a conservation of knowledge in your book. I thought could these two questions related, but I'm not sure. Thank you.
Yeah, well, so I think this conservation of knowledge and that kind of thing happens where there's not only quantum theory, but closed time-like lines as well. So just setting that aside for the moment, quantum computation never involves stealing anything from other universes. It's always a collaboration, but not only a collaboration, it's a collaboration between different versions of the same people that started the computation. So somebody programs the computation, and that programming happens in a certain range of universes. Then, as the quantum computation proceeds, that range of universes, which were initially identical, with everybody putting in the same program and wanting the same answer, wanting the same number factorized or whatever. And then as the computation goes on, this range of identical universes differentiates itself into a vast, vast number of different universes, all performing a different computation. And then they are recombined, but not all with the same phase. So in such a way that they all, well, in some, for some algorithms, it's not all, it's just most, but let's say in a simple case, they all end up with the answer. So there's no stealing going on. They have entirely, but not only are they collaborating, but they're collaborating on the same problem.
Hi. Recently in your conversation with Robin Hanson, you said that the problem of a Y risk and frequencies can be approximated by probabilities is an unsolved problem.
Yeah.
And I was just wondering how come the quantum theory doesn't solve that problem, or why isn't it that probabilities are just frequencies in the multiverse?
Yeah, very important question. It's because when you're betting on roulette or something like that, which we can be approximated as a quantum process, what you mean by using probabilities is that you'll get a different answer in different universes. But when you bet on, let's say, one company over another, you're not betting that the company that like, suppose you have you can bet on two companies and you're wondering which one of them is going to make more profit than the other or give a higher dividend than the other or whatever. It's not that you're expecting the universes to divide equally, supposing its risk is 50-50. You're not. You're saying that you don't know how they're going to divide. In fact, you might be fully of the opinion that the universes aren't going to divide very much with respect to which company is better. That one of them is unequivocally better, but you do not know which it is. And that ignorance is somehow translatable into a probability, but that violates the theory of probability. The deriving knowledge, including knowledge of probabilities, from ignorance is a cardinal mistake in probability theory. So it's not that. It must be that there is some way of dealing with knowledge which gets you to say a rational decision, and then you can work backwards and say, well, because that's the rational decision, the implicit probability must have been so and so. By the way, there are other cases where using probability and using classical decision theory at all is a mistake. So this decision making in the decision making under real ignorance, and decision making under probability doesn't hold. And really, the only thing you can say is, I don't know. And you have to resort to other objectives, such as minimizing your maximum loss or maximizing your minimum gain or whatever, or just to keep out of it if you can. So I don't know. As I say, it's an unsolved problem. Did I understand your question correctly? I mean, you said, why isn't it the same? Well, for probability to make sense according to quantum theory, it must be because things are distributed in a certain way in the multiverse. It cannot possibly work when it isn't distributed much in the multiverse, but you just don't know.
Yes, I think you understood it correctly.
Okay, well, tell me if you have the answer.